So let's talk about a couple of hints for the homework and some of the other properties that you may want to be aware of when dealing with Legendre polynomials. In problem 4 from 105, I think. Yeah, so let's take a look at problem 4 from 105, in which you have to compute some coefficients of the Legendre series related to the function 0 for x between -1 and 0 and x for x between 0 and 1. The first question is to they say, okay, why does it have a Legendre series? And remember, just like the Fourier series, one can prove that any piecewise defined function, piecewise continuous functions, will have a Legendre series. So, skip that part. There's not much to say because we assume this to be proved for all of these series that we dealt with in this class. And in part B, the question is to prove that the odd coefficients of the Legendre series, which let's remember a2m plus 1, that's going to be so the Legendre, hold on a second, let me see, series in part A. Yeah, so remember the formula for an is 2 over 2n plus 1. Just a second, I got that. I'm going to check something. A2n plus 1. I'm trying to see if it says about the Legendre series, even or odd. Look at the book a little bit. Pattern theorem 1. Yeah, so the full Legendre series. So that's going to be 2n plus 1 over 2 minus 1 to the 1. I mean, the integral from -1 to 1, f of x, pn of x, dx. Okay, so the question in this problem is to show that the odd coefficients for this are equal to 0. So you need to show this. So what I want to point out is that if you have to show that this is equal to 0, you don't have to bother with these coefficients, because normally, again, if now the index is 2n plus 1, you'll have to replace 2n plus 1 for n over here. So it becomes, 2 times 2n plus 1 plus another 1 over 2, from -1 to 1, and then the other integral. But in this case, just look at the integral from -1 to 1, because you need to prove that this is equal to 0. F of x p2n plus 1 of x dx is equal to 0. So this is what you have to show. Now, because the function is piecewise from -1 to 0, from -1 to 1, and then 0 from -1 to 0, this integral is going to be from 0 to 1, because the first portion is 0, x p2n plus 1 of x dx. So you basically have to compute this integral between 0 and 1. And I mentioned this before, but one more time, if you look at the recursion formulas here, just make sure you make that substitution carefully, because that's the tedious part. So you first have to use this formula, x p2n plus 1. So that means you replace n with 2n plus 1 everywhere in that integral. So we have the integral from 0 to 1, and n is 2n plus 1. So try to do it in your mind to speed up the process a little bit. But now I want to emphasize the substitution, just to be clear. How you replace n with 2n plus 1 everywhere in the formula. So basically this splits into two integrals, right? It will be 2n plus 2. On the bottom is 4n plus 3. P 2n plus 2. And the other piece will be 2n plus 1 over 4n plus 3 again. P2n. All right, so that's your new integral. And you can take these two integrals separately if you want to, or you can go ahead and distribute the coefficients. But now this splits into 2n plus 2 over 4n plus 3, the integral from 0 to 1, p2n plus 2 of x, plus 2n plus 1 over 4n plus 3, the integral of p2n of x. And then the other recursion formula for each of them. Yeah, so let's say, for example, you continue with p2n of x, right? So you go back to the second formula and replace n with 2n. So the way to do this, let's write it separately here. The integral from 0 to 1 p2n of x will be the integral from 0 to 1. I go back over here and replace n with 2n. So it's going to be 1 over 4n plus 1 p prime 2n plus 1 of x minus p prime 2n minus 1 of x. And at this point, notice that the case n equals 0 is to be treated separately. If you do everything correctly, you will basically have your answer in terms of these polynomials evaluated at 1 and 0. Remember, at 1 is 1, and at 0, if you have basically odd ones at 0, that's also 0 as well. So remember, an odd polynomial at 0 is 0. Any polynomial, odd or even, at 1 is equal to 1. So if you do this problem correctly, both of these integrals, this and this, will be in terms of odd polynomials. And when you plug in 1, you'll end up with 1 minus 1 in this antiderivative. And when you plug in 0, it's going to be 0. So give it a try. And before I talk about another homework problem, let's establish some remarks in terms of the possible value of this integral, right, when you multiply a function by a Legendre polynomial. It's worthwhile again to remember how an odd function looks like on a symmetric interval, right? So if you have an odd function to integrate on a symmetric interval, the answer is always 0. And let's say you have an even function multiplied by an odd polynomial. This becomes an odd function. So we can write equal to 0 right away without too much fuss. Right? If I plug in minus x for x, if f is even, that's only f of x, and you pull out the minus if you have just odd coefficients in the Legendre polynomial. By the same token, if you have an odd function multiplied by an even polynomial, this is again an odd function, this multiplication of the two. And this will be again 0. So an odd function will have a trivial representation, basically, if you have to compute its even Legendre series and vice versa. You know, if you have an even function and you look at the odd coefficients for the odd Legendre series. There is another important result which is worthwhile to know when you actually have polynomials, just regular polynomials instead of a function f of x. So for example, in the case when you integrate powers of x. And that is the point of problem 10. So let's talk about 105 problem 10. This looks a little bit harder than it is in reality. The goal is actually part B. So the goal is to show that when you integrate a polynomial multiplied by a Legendre polynomial, so P of x is just a polynomial of degree less than n. Then the integral of that polynomial times Pn of x is always 0. Again, between -1 and 1, not for other bounds. So basically, if I have, for instance, the integral from -1 to 1 of x third minus x plus 7, let's say, and then multiply by the Legendre polynomial P5 of x, then the answer is always 0. As long as the degree of the polynomial that appears in this integral is less than the degree of the Legendre polynomial, then the integral is 0. So that is the goal of problem 10, to actually prove why that happens. That's actually an application of orthogonality. Let me give you a couple of hints of what they talk about in the first part. So essentially the part A gives you some sort of guidelines on how to show this property. So it says that recall that Pm of x is a polynomial of degree m containing only the powers x to the m, x to the m minus 2, x to the m minus 4, and so on. So let's say there are essentially two cases, right? So let's say you have an even degree, right? Then the Legendre polynomial of this degree only has the powers x to the m minus 2, all the way up to x squared, x to the 0, which is of course 1. And you can use this to show that you can write x to the m, basically x to any power, in this case an even power, in terms of Legendre polynomials of that degree and less. So in part A, the question is to show that you can write x to the m as a combination between some constant Pm of x plus some linear combination of lower degrees. This simply comes from rewriting x to the m from what the Legendre polynomial is equal to. So for instance, if you have the Legendre polynomial itself, so this is what you have to show in part A. So if you have the Legendre polynomial Pm as am x to the m plus am minus 2 x to the m minus 2 up to a naught, you know, this relation that they talk about in the problem is obtained by simply getting x to the m by itself. So basically you want to move all these guys to the left and then divide by am. So on one hand you have am x to the m equals Pm of x minus am minus 2 x to the m minus 2 all the way up to a naught, and then divide by am, and just to match what they say in the problem, basically this becomes the constant c, this becomes the constant cm minus 2, c naught, and so on. So again, I think this is a little bit confusing in the problem because it's not clear what are these coefficients, c, cm minus 2, cm minus 4. These are simply renotations of the coefficients that you get when you write x to the m in this format. Now, what's the purpose of it? Because it's not obvious what the purpose is of all this. You can repeat the argument for all the other remaining powers of x. So x to the m is a coefficient times Pm. By the same token, let me write it on the next page. So you write x to the m as some coefficient pm of x, and then a bunch of coefficients involving lesser powers of x. But then you can repeat the process, and you can say, okay, x to the m minus 2 is itself equal to some other coefficient, let's call it d, pm minus 2, and then some other, I think this is plus in the way they wrote it in the book, and then plus some other coefficients, let's say, you know, e m minus 4, x to the m minus 4, and so on, right? So in the end, x to the m can be written as some linear combination, let's call it cm, pm, cm minus 2, pm minus 2, so a linear combination of even Legendre polynomials. Okay, so any x to the m with m even is a linear combination of even Legendre polynomials of degree m and less. And when you figure out the conclusion, I mean, how do you prove that the integral of any polynomial of degree less than n multiplied by a Legendre polynomial of degree n is equal to 0? When the time comes, for instance, to integrate, let's say, x to the m times Pn of x dx in the interval minus 1 to 1, this integral basically is going to be a combination of integrals involving these Legendre polynomials, Pm, Pn, and then Pm minus 2, Pn, and so on. And as long as m is not equal to n, or m minus 2 not equal to n, because of the orthogonality, we know that these integrals are equal to 0. So it's actually a bit messy because of these renotations of the constants, but that is the main idea of the problem. See if you can actually organize the solution one way or another in a clear way, and if that doesn't make sense, let me know during the office hours. But again, the bottom line is that any power of x, because you can, by the way, you can repeat the argument for m is odd, same idea, right? So any power of x, let's say x to the m, can be written by a combination of Legendre polynomials degree m and less. So then when I integrate x to the m times any other Legendre polynomial, well, if this m is less than n, I'm guaranteed that all of these pm, pm minus 2, and so on will have a different index than n. And so as long as these polynomials are different, when you integrate this product, we know that from orthogonality on minus 1 and 1 that the integral is 0. So basically, this result shows that if you integrate, or if you find the Legendre series of a polynomial, all of the coefficients corresponding to x of power less than n will be 0, right? So when you integrate p of x times pn of x, all of the coefficients less than n will be 0. So that's it for today. Make sure you go over these problems as soon as possible so we can talk about it during the office hours. And if I don't have another lecture, then I thank you for your attention, and hopefully maybe some other time we'll do more on this topic depending on the need or the interest. Because this one was kind of improvised due to the circumstances, and maybe it would be a nice idea if we do it on the light board. We'll see how what the future will be. Though for this topic, it's not that easy actually to use the light board because of the space. limitation. But thanks for your attention, and I'll talk to you soon.